EMF versus potential difference. So what is EMF? It is electromotive force. Okay, so this is the potential which is generated by a cell when there is no current flow. That means there is no electron flow. So there will be no current, and that is, it draws no current. But what is potential difference? Though these two are very, that is, their meaning is very close to each other, so there is a chance that of confusion. Okay, so we have to be careful that there is a very slight difference between these two. So EMF is the potential that is generated by a cell when there is no flow of electron, that is, it is drawing no current. But potential difference, it is the difference between the electron potential of the two electrodes when the cell is under any condition. That means now there is electron flow. Okay, so we can say that EMF, it is as if the theoretical value, and the potential difference, which is the actual value when the cell is under operation. Okay, and when the cell is not under operation, then the potential, we will call it as EMF. So what is the difference between these two? So here we have 4 points. It is a potential difference between the electrodes when no current is flowing in the circuit. But when the cell is under operation, then the corresponding difference in the electrode potential, that will be called as potential difference. So it is a maximum voltage that the cell can deliver. And remember, this is theoretical. Because what is the theoretical value, that is the maximum voltage it can deliver, in actual process, it is always less than the maximum value. So potential difference, that will be always less than the maximum of the cell can deliver. So this is actually the practical situation. Okay, because in practical situation, whatever potential difference we are getting, that is always lesser than the theoretical value. The theoretical value is EMF. EMF is responsible for the steady flow of current in the cell. So as there is difference, so that is why the current is flowing, so that the difference is decreased. Now it is not responsible for the steady flow of current in the cell. This is responsible because when the cell is not under operation and there is potential difference, that is why there is a flow of current. But once the flow of current, that is flow of electron, it is started already, then it is not responsible for the steady flow of the current in the cell. And the last difference is the instrument by which these two are measured. EMF is measured by potentiometer, but potential difference is measured by voltmeter. Okay, so this is the very minute difference between EMF and the potential difference. Though both are used sometimes for generating the same meaning, but we have to remember that there is a very slight difference. These two are not exactly same. Now, different types of electrodes may be there. So until now, the examples that we have seen, in most cases there is metal electrode we have seen, or platinum electrode, which is also metal electrode, but the difference is, in case of platinum, it is inert electrode, it is not taking part in the reaction. But except that also, there may be some other types of electrodes. So we will see that here. First type we have here, ion and gas electrode. So for example, we have taken platinum, then chlorine gas, 1 atmosphere. Because it is gas, so obviously it will be expressed in pressure unit. And Cl minus, which is aqueous, that is in aqueous condition, chloride ion is present and its concentration is given 1 molar. So ion gas electrode consists of a gas. It may be hydrogen, chlorine, oxygen. So these are some of the examples. Here we have taken the example of chlorine. Now this is in contact with a solution containing the ions which we can derive from the cell. So the ion that we can derive from the cell is Cl minus. Similarly, if we have taken H2O, then the ion that we can derive from it, it will be H plus. Similarly, for oxygen, it will be O2 minus. So it means, or HO minus. So it means that there will be a gas and there will be ion which is basically coming from the, that is which is also present in the gas, that is the same ion. And here, as no metal is involved in this half reaction, but Cl minus, that is after losing electron it will be converted to chlorine. Now this chlorine gas, that will be deposited in the platinum electrode. So that is why we have taken platinum electrode, which is inert electrode, because if we have not taken it, there is no solid electrode, I mean that is electrode, it must be some kind of rod. Okay, so if it is not present, because here the system is producing gas, but gas cannot itself be directly, we cannot use it as electrode, it must be something solid. So that is why we are using this metal, which is not taking part in the reaction, it is just providing the space so that this gas can be deposited on this electrode. Okay, so it is not, its role is not to take part in reaction. So platinum is not taking part, it is just inert electrode. And here potential depends upon the concentration of its ions, that is whatever is the concentration that will be mentioned, and also the pressure of the gas. Okay, so here we will have ion, and also this ion which is derived from some gas, so that is why the name is ion gas electrode. Okay, next type is metal sparingly soluble metal salt electrode. Now sparingly soluble means it is not very soluble, very slightly soluble, and there will be a metal also. So here we have silver metal, now it is solid, so that is why S is written in the bracket, that is its physical state, and AgCl, which is sparingly soluble, so that is why it is S, because it is not suppose if it is KCl, then it is fully soluble, in that case we can write aqueous, but here it is soluble. So it is also known as reversible anion electrode, because here the anion that is present, that is Cl minus, that can remain in equilibrium with this AgCl. So that is why reversible anion electrode. In this case, a metal which is in equilibrium with a solution containing the same anion. So here this is the electrode. In the previous case we have used platinum electrode because here gas is generating, but here we are getting solid Ag, so we don't need platinum. So this metal, it is in equilibrium with a solution, okay, which is containing the same anion. So this solution, it is containing the same anion which is also present in this AgCl salt. So that is why it is metal sparingly soluble metal salt. So AgCl is a sparingly soluble metal salt, and the metal is silver. Fine. The third type is metal ion. Now this is comparatively simpler. If you check with the other two, it is very simple, because here we have simple the metal which is itself the electrode, solid zinc, because it can act as rod. Okay, we can dip zinc rod. So this is electrode, and the corresponding ion, that is cation, is Zn2 plus, which will remain in the aqueous solution. So we are calling it metal ion. This is the metal, this is the metal ion. So metal strip, it is kept, strip or rod, whatever, it is kept in contact with the solution of a water soluble salt containing cation of the same metal. So suppose you have dipped zinc rod in zinc nitrate solution or zinc sulfate solution, then that is the example of metal ion electrode. It is in solid state because we have taken the metal strip, but it is in aqueous state because cation, whenever you are mentioning any cation or anion, it must be in aqueous phase. Okay, that is solution phase. Last one is redox electrode. Now it is we should not say that it is the last, because there may be some other types, but these four are the most common. Fine. In this case, from the name you can understand that an inert metal, that is Pt, it will be dipped in a solution which is containing ions of an active metal. Why we are calling it active metal? Because here Pt is not active, it is not taking part in reaction, it is just playing the role of inert electrode, just like you have seen in case of the first type, that is ion gas electrode. So here platinum is dipped in a solution containing ions of active metal. So tin is the example in two different oxidation state. Now Sn, it is present in two different oxidation state. So one will be oxidized from, that is 4 plus, another is reduced from, that is 2 plus, that is why it is redox electrode. So same element in two different state, same metal in two different oxidation state. Now see, as both are cation, that means both are in aqueous solution. Now when both are in same phase, normally we use this step comma, but here we do not have any Sn0, that means Sn in neutral state, that is not present. So obviously these two cannot be in solid strip or rod like nature. So that is why we have to use this inert electrode platinum, because here tin, as it is not present in zero state, oxidation state, so that is why it cannot act as electrode, metal electrode. Okay, so that is why platinum is used. So these are the mainly 4 types of electrodes, but there may be some other types, but these are the most common. You will see the examples, that will be any of these 4 types. Now here we have some cell representation. So from this cell representation we can write the corresponding half reactions, that is the reaction which is taking place at anode, one half reaction, another half reaction which is taking place at cathode. So we can write first these two half reactions, and then when you will add these two, you will get the overall cell reaction. Okay, and for individual half cell reactions there will be a value for electrode potential. So when we combine these two values, we will get the electrode potential of the final system, that is the overall reaction. So in this cell representation, here we have zinc electrode, then in the solution phase there is ZnO2 2 minus ion, and there is another ion present which is HO minus. So it means that here zinc, this side is obviously anode, because by default when you have any cell representation, in the left hand side there will be anode and in the right hand side there will be cathode. Now here Zn, it is oxidized to ZnO2 2 minus, because here the oxidation state of Zn is 0, but here it is plus 2. So how to understand that it is plus 2? Because here overall charge is 2 minus, and for each oxygen atom it is minus 2 charge, and you have 2 oxygen atoms, that means it is minus 4 charge, and 2 minus charge is extra, that means the positive the oxidation state of Zn, it will be plus 2. So from 0 state it is converted to plus 2, that means it is oxidized, and it is in basic medium, which is clear from this HO minus. And this type of double, that is parallel sign, it means there is a salt bridge. So in another section in the right hand side, here Hg2O, it is reduced to Hg0. So this is Hg0, and Hg2O, oxygen is having minus 2 charge. So for each mercury there will be positive plus 1 charge. Okay, so from plus 1 state it is converted to mercury 0 state. So what will be the reactions? So at anode we have, it is a complete balance equation. Okay, now if you are wondering that why how we can get it, then it will be like this. Suppose we have first write Zn, and then it is converted to ZnO2 minus. Now when you have written ZnO2 minus, so it is 2 minus. To balance the oxygen atom, we have to add 2 HO minus. Now when we are adding 2 HO minus, we also have to add 2 H plus in the right hand side. Now we cannot write H plus because it is not in acidic medium. So what we will do, to balance this H plus, we will add 2 HO minus both sides. That means it will be 4 HO minus. Okay, now we have to balance the negative charge. How to balance the negative charge? It is very easy. In the left hand side we have total 4 negative charge, and in the right hand side these two will cancel each other. So overall in the right hand side there is 2 negative charge. So 4 negative charge in the left hand side but 2 negative charge in the right hand side. So to balance charge we have to add 2 electrons. Okay, and this is anode reaction, so this is oxidation reaction, so obviously electron will be on the right hand side because Zn has lost electron after the reaction, so that is why electron it will be on the right hand side. So this is the reaction overall, because here we will have Zn plus 4HO minus, then in the right hand side ZnO2 2 minus, and these two together will make 2H2. Now if you are thinking that here we have 2H2 and 4H2, but ultimately if you subtract 2H2 from 4 it will be 2H2. So basically we are getting the same equation as it is written here. Okay, and for the second reaction here Ag2O, that is converted to mercury. To balance Ag we will add here, multiply it by 2, and to balance oxygen it will be half O2, and to balance, that is if we want to balance the charge then it will be 2 electrons. Now see what we will do, we will add these two equations. So when we are adding these two equations, what we are getting? We are getting this overall cell reaction. So in the overall cell reaction there is Zn 4HO minus, that is this one, then 2Ag2O, sorry it is not 2Ag2O. Then in the right hand side we have ZnO2 2 minus, 2H2O, this one, and 2 mercury and half oxygen. And here the physical state, wherever it is applicable, that is also mentioned. So here as this ion is directly mentioned in the cell representation, so we can write it. If there is 2 negative charge, that is not a problem. Fine. The next one is PtCl2. Let me erase it. Here you can see the example of ion and gas electrode. Okay, this is metal ion, the first one, and this is ion gas electrode, where we have just discussed the types of electrode. So you can see here the example. Now here normally in the anode we know that there is oxidation. So chlorine is basically in zero oxidation state, but its reduced state is Cl minus. So you will see that in the anode normally the reduced state is written first and then the oxidized form is written, because ultimately in the overall reaction the species which is in anode, as there is oxidation going on, so the starting material always written first and then the product. But in case of gas, and that is gas and its corresponding ion, whenever this type of situation you will see, then it is chlorine which is written first. Now this is the oxidized species because it is 0 and this is -1. This is the oxidized form, this is the reduced form, but still it is written before because here the gas that is generated, that is associated with the platinum electrode. It is deposited on platinum surface. So that is the reason it is written just beside platinum. Otherwise the reduced form is always written first, just as you have seen in case of the first cell representation, where Zn, its reduced form is written in the left hand side and then Zn2 plus form is written, which is this ZnO2 2 minus R, but ultimately it is Zn2 plus, that is the oxidized form. So in this case, as chlorine is generated over platinum surface, so that is why chlorine is written first. So in the anode there is conversion of Cl minus to chlorine. So Cl minus, it will lost electron and it will be converted to chlorine. And in the right hand side, after salt breach, we have K2Cr2O4. So K2Cr2O4, we have the ion Cr2O4 2 minus. Okay, so Cr2O4 2 minus, we also have another salt, which is Ag2CrO4 2 minus. Now in both cases, that is here, if we have to compare the oxidation state of silver, because we have the electrode which is silver, it is in zero oxidation state. That means here its oxidized form is Ag plus, which is present here. This is actually Ag plus. So here the main species which is involved in the reduction reaction, because it is cathode, Ag plus is accepting electron, it is converted to Ag, that is reduced to Ag. So here we are not concerned about the anion, because in both cases you will see chromium, its oxidation state is same. Okay, Cr2O4 2 minus, and it is 2K plus. It is, if you just focus on this part. So what will be the oxidation state of chromium? For oxygen, for each oxygen it is -2, so -2 into 4, it is -8, and here we have charge 2 minus, that means chromium oxidation state it must be 3. Okay, 3 into 2 it is +6, and 4 into -2 from oxygen it is -8, so overall 2 negative charge extra. And similarly, if we see in the right hand side, here we have the anion CrO4 2 minus. Okay, so this, in this case the oxidation state is basically, sorry, it is +6. Okay, but why it is +6? Because here the anion is CrO4 2 minus, because we have 2 Ag plus, so 6 plus charge from chromium, and from oxygen we are getting -8 charge, that means 2 negative charge extra. So here chromium, that is oxidized to Cr6 plus, but as here we have electrode Ag0 and the cation Ag plus, so that is why we will consider this is as the actual species which is involved in the reduction reaction, that is the species in the cathode. So here the cell reaction that will take place is, this side is, this is anode reaction, 2Cl minus in aqueous state it is converted to chlorine, and this chlorine will be deposited in the platinum, and here electrons lost by chlorine. Okay, now Ag2CrO4, here oxidation state is +1, it is accepting 2 electron, that is why it is now converted to 2 Ag plus, and CrO4 2 minus, that is as present as it is. So here in the actual reaction that we have written here, now you can understand that in this anion CrO4 2 minus, here the oxidation state is +6, this is also +6. So that is the thing I actually wanted to say at that time. Don't consider this salt, you have to focus on this salt, because here silver is included, and in the salt of silver CrO4 2 minus, this anion it is intact, it is CrO4 2 minus, so oxidation state of chromium is same, so the actual species which is reduced it is silver, not chromium. Fine. So the overall reaction will be electron will be cancelled, and also see both side charge is same, so it will be 2Cl minus, overall reaction Ag2CrO4, and this side we will have chlorine and CrO4 2 minus. Okay, let me erase this. The next one is platinum, again inert electrode, because if you look at the cell representation, it is the last type of electrode that we have discussed in the types of electrode, which is redox electrode, because same species, that is same metal in 2 different oxidation state, tin in 2 different oxidation state, so that is why in both cathode side and anode side there is presence of inert electrode PT, because here we do not have iron in 0 oxidation state, and also we do not have Sn in 0 oxidation state, so that is why we have to take inert electrode which is platinum. So in the anode, the reaction that is going on is Fe3 plus is 2 plus. Fe2 plus, it is converted to Fe3 plus by losing one electrode. This should be written next actually. This is 2 plus, this is 3 plus. Okay. And the reaction at cathode, that is the reduction reaction. This is cathode, this is anode. So here the reaction will be Sn4 plus is accepting 2 electron and it is converted to Sn2 plus. So both side charge is same. Now to balance the, as we will add these two equations now, but electrons should be, number of electrons should be same. So that is why what we will do, we will multiply the first equation both side by 2. So now the electron can be cancelled. So ultimately the reaction becomes 2Fe2 plus plus Sn4 plus, that is converted to Fe3 plus and Sn2 plus. So here iron 2 plus, that is oxidized to iron 3 plus, and tin 4 plus, that is reduced to Sn2 plus by accepting electron from iron. So iron, it has lost electron, and tin 4 plus, it has gained electron. Okay. Here we have a problem. The chemical reaction 2AgCl aqueous plus H2 gaseous, and in the right hand side we have HCl and silver solid. Now the reaction is given and we have to identify that which cell representation, as it is given here 4 options, which cell representation is actually correct. So it is the reverse case. In the previous case there is cell representation given and you have to write the half reaction, overall reaction, but now the overall reaction is given, we have to write the cell representation, which is correct. So first of all you have to understand that which species is reduced and which species is oxidized. So here oxidation state of silver is plus, in the right hand side it is 0 because it is metallic silver. In the right hand side H is plus oxidation state, here it is 0. That means this is the oxidation reaction and this is reduction. So silver plus to silver 0, that will be present in the right hand side. Now if you look at the options, in all the options it is at the right hand side, so there is no problem. And H plus hydrogen system, that will be in the left hand side, that is the anodic side. Now as it is ion and gas electrode, so that is why we have to use inert electrode. So that is present in all the options, which is correct. So if you see this part, that is the reaction at the anode, that is same in all these options. So there is nothing wrong. But after that, if we look at the right hand side, here in the first case we have 1 molar KCl, that is Cl minus ion, then AgCl solid. So it is not electrolyte, it is solid. It is, if it is in soluble, that is solution state, it must be Ag plus, because if it is not very soluble salt, it is sparingly soluble salt, it will mostly remain undissociated. But only dissociated state, that is Ag plus cation, that we have to consider. But here it is mentioned AgCl solid and this is electrode, that is fine. These three are same. Only in the last case we have AgCl solid, but actually silver will be the electrode. So here you can easily cancel this one. Now among these three, as here that is Ag plus, that is not mentioned because there must be the presence of this cation Ag plus, because it will accept electron which is lost by hydrogen. But in option A and option C and also in option D, there is, in all these cases it is AgCl solid, it is not in solution state, so that is why it will not be correct. But if you look at option B, here 1 molar Ag plus in bracket physical state is aqueous. That means it will be correct. And you can also write it in this way, that as here HCl aqueous is present. So if it is written as AgCl, then also it is fine, because the Cl minus it is written here separately. So it is correct expression, but there may be another expression which will also be correct, and here it is, you can see two things are written, two cell representations are written. So this is which is present in option B, the second one. This is 1, this is 1 and 2. So 2 is basically present in option B. So option B is actually the correct option, because we have to mention Ag plus aqueous, but you can also write it as if 1 molar H plus. So this Cl minus, you can also write it here, but in that case you have to write AgCl in bracket aqueous, because AgCl in bracket solid is mentioned in all this, which is not correct. But if you are writing AgCl aqueous, that means it is that AgCl which is in soluble state, that is dissociated state. So one way you can say that it is actually nothing but Ag plus and Cl minus in dissociated form. So this can also be correct, we cannot say this is wrong, but obviously the second representation is better, because here directly we can see the Ag plus cation. Okay, so here correct option will be option B. Now we have to know some terms which will be used frequently, and we have already used some of this, but now we have to know what is the actual meaning of all these terms. So single electrode potential, it can also be written as ACP. Okay, so single electrode potential, from the name single, it means that it is the electrode potential of one system, it is not the overall electrode potential. So this is a measure of tendency of a metallic electrode to lose or gain electrons when it is in contact with a solution of its own salt. So suppose you have a metal M and its salt, that is M2 plus, so it may be converted from M to M2 plus, or there may be the opposite tendency, that is it will accept electron and it will be converted to metal 0. So from this single electrode potential we can understand that whether the electrode, it will have a tendency to lose electron or gain electron. That idea we can get from single electrode potential, because this is a measure of the tendency of this electron gain or loss. So this is single electrode potential. Now, in order to compare the electrode potential of various electrodes, suppose there are single electrode potential of several systems. So what is necessary? It is necessary to specify the concentration of ions present in the solution in which the electrode is dipped. That means you have to mention the concentration of the scatter, and also we have to mention the temperature of the half cell. Why? Because electrode potential is dependent on the concentration as well as the half cell. So suppose there are three systems, you have ACP of three systems, 1, 2, 3. You are comparing three different metal systems. But if you have not kept the temperature and concentration of all the metals, suppose it is metal 2 plus, it is metal prime 2 plus, this is metal double prime 2 plus. So if you want to compare the ACP of these three, you have to keep the concentration of all these cations same, and also the temperature of the half cell should be same. Then only you can compare, right? Otherwise comparison will not be correct. So for that, what we have done, we have fixed a standard condition, because if there is no standard condition fixed, then how you will compare the electrode potential? So that is why now the next term that we have to know is standard electrode potential. Okay, single electrode potential, standard electrode potential. So now what we have done, we have fixed the temperature at 25 degrees centigrade and the concentration is fixed as 1 molar. So this is a measure of tendency of a metallic electrode to loss or gain electrons when it is in contact with a solution. So up to this, it is the same definition that we have written, but here it is written with a solution of its own salt. Here no concentration, no temperature mentioned. But now we have mentioned a fixed concentration and fixed temperature. So that is why it is standard electrode potential, because now our condition is standard. So with respect to this standard, we will compare the single electrode potential of different system. Now it is possible, because these are the variables. So if you have not, if you are not making the variables constant, you cannot compare. Now, according to IUPAC convention, the reduction potential alone can be called as electrode potential. So if it is directly mentioned reduction potential, that is RP, then it is fine. But suppose if it is mentioned only in electrode potential, in the numerical or in the book, you are reading something and it is mentioned electrode potential, then what we do, according to IUPAC convention, we consider it as if it is reduction potential. This is the convention. Otherwise there will be problem, because if in some places we are using reduction potential, in some cases we are using oxidation potential, there will be problem. Though both are having same numerical value, only the sign is opposite, but still it should be fixed. So for all system we will always use the reduction potential. Okay, that is M2 plus, it is accepting 2 electron and we are getting M. So this is the reduction method. So in this half reaction, the electrode potential that we will get at standard state, that will be called reduction potential. You can also call it electrode potential. And the given value of electrode potential, it will be regarded as reduction potential unless it is specifically mentioned that it is oxidation potential. That means if oxidation potential is not mentioned specifically, you can consider the electrode potential of the system as reduction potential. And this is a convention according to IUPAC. Now to measure the single electron potential, we need a reference electrode, because you cannot measure the potential of individual half cell directly. You can measure only the difference between two half cell potential. So we need a reference electrode. So this electrode whose potential is arbitrarily fixed, so we will fix the potential for the electrode which will be considered as reference electrode. It must be arbitrarily fixed or exactly known at a given temperature, and that will be known as reference electrode. So here we have two examples. One is standard hydrogen electrode, in short She, and calomel electrode. So mostly we will discuss this one. This is the most commonly used, She. So standard hydrogen electrode, where the system is basically H plus H2 system. So its reduction potential by convention, it is considered 0 volt, and we will compare all the other half cell which is attached to She, that is standard hydrogen electron, and then we will measure what is the electrode potential we are getting, that is the corresponding voltage that will be generating in the circuit. That will be treated as the overall electrode potential. But as this H plus H2 system, so it is one half of the, that is half of the overall reaction. Okay, so now you know the overall electrode potential which you will get from the galvanic cell, and you also know what is the reduction potential of one of these half reaction. So obviously now you can get the electrode potential of the other system, because two values are known, only one is unknown. So now we will see that how by using reference electron we can measure the standard electrode potential. So measurement of standard electrode, it will be potential. So electrode potential of a particular single electrode can be measured only with respect to reference electrode, standard reference electrode, SRE. Okay. Now SRE, the SRE against which, that is the standard reference electrode, against which we will measure the electrode potential of all the other single electrodes, it is mainly used is standard hydrogen electrode, that is SHE. Now in this SHE system, the electrode in which pure and dry hydrogen is bubbled at 1 atmosphere. So here we have to fix all the concentration and pressure terms. That is, we have to be sure that they are in standard state. So what is the standard state we have considered here? As the system is H plus H2, so partial pressure, it must be expressed in ATM. So it is taken as 1 ATM. Temperature is 25 degrees centigrade, that is 298 Kelvin, on a platinized foil, because inert electrode is platinum, through a solution which is containing H plus ion. So we have to use any acid at unit activity, that means concentration, it is 1 molar. Activity, that is, you can also consider its concentration, so it will be 1 molar. Temperature maintained at 25 degrees centigrade. Now by international agreement, the standard hydrogen electrode, that is for She, the arbitrarily chosen value of potential is 0. Fine. So the She thus obtained from one of the 2 half cells of a galvanic cell. So it is one of the 2 half cell of the overall reaction. So She, its reduction potential considered as 0. Overall potential we can measure from the, we can see it in voltmeter, and in this way when we will consider these 2 values, we can easily get the unknown electrode potential of the other system, that is the other half cell. Now the question may arise whether She will be anode or cathode. Now see, it depends what type of other system you have taken. So depending on that, She, it can have a tendency to lose electron. In that case it will be in the anode system, because oxidation, that means H2 will be converted to H plus. But it can also act as cathode, that means now H plus will accept electron and it will be converted to H2. So it depends on the tendency of the other system, whether it has higher capacity to lose or gain electron compared to the hydrogen system's gain or loss electron capacity. Fine. So look at this picture. This is the picture of basically She. So this is one of the half cell, She. It is not the overall cell. So try to understand the picture. Platinum electrode is taken, that is platinized foil, and this is connected to this hydrogen gas outlet, and hydrogen gas that is passed through this channel. Okay, and PT wire is also present. Now the electron that is coming here, electrons is coming here. So this electron, now it will be accepted by H plus ion, because H plus ion that is present in this solution. Now if you look at this picture, so this small region, it is now, you can see it is zoomed. So H plus is accepting this electron. So this is the surface of platinum. H plus is accepting this electron and it is converted to H2. Okay, so that means there will be bubbles of hydrogen. So these are the bubbles of hydrogen. Okay, so at the surface, this electron gain and loss process that is going. So this is one of the half cell, that is She. It can be cathode, it can be anode. So when it is in anode, in both cases it is 0.0 volt. But when it is in anode, it is losing electron, that is She hump reaction. And when it is in cathode, it is accepting electron and converted to H2. Okay, so depending on the other system, it can act as anode or it can act as cathode. So now we have taken particular example measurement of standard electrode potential. That is, now we are measuring ACP, and we are measuring ACP of which system? We are measuring the ACP of Zn2 plus Zn system. So for that, what we have taken? We have taken zinc nitrate solution. So here we have zinc nitrate. That means in the medium there is presence of Zn2 plus ion, and as here in the voltmeter the value that we are seeing, that is 0.76. That means it is positive. Now electron flow, it is from zinc anode towards She cathode. So here She is behaving as cathode. But how to know whether it will behave as cathode? Because if the metal, it has high negative potential, then it will be, She will be acting as cathode. But basically, whether this metal has high negative potential compared to She or not, that is, high negative means what? She is having 0 volt. So the other system, if it has some negative value, that means it is lesser, having lesser reduction potential value compared to She. So that means it will be acting as anode. That is, it will lose electron. It will lose electron, and that electron will be accepted by H plus. Now how to understand it? Here, after setting up this cell, what we are seeing? We are seeing that electron flow, that is from zinc towards hydrogen system, that is She. That means the direction of current is opposite. Direction of current is this side, because electron flow direction and current direction, these two are opposite. So if electron is moving from anode to cathode, that means current is in opposite direction. So which can be understood from this cell. When we will perform this cell process, we can understand that electron is flowing from which side. So as it is flowing from zinc side, that means zinc has lost electron, and that is why it will be anode, and She is cathode. It is negative, it is positive, because in galvanic cell, that is the convention we follow, that is zinc ion, it will be treated as negative sign. And here we have also salt bridge where NaCl is present, because salt bridge, its presence is necessary. We have already discussed the role of salt bridge. It helps to maintain the electrical neutrality. In the left hand side, this is the oxidation reaction. In the right hand side, this is the reduction half cell reaction. And if you add these two reaction, electron will be cancelled, and you will get, this is the overall cell reaction. So remember, finally from this 0.76 value, so now you can see it in the voltmeter, this value will be appearing in the screen, and you also know what is the potential for She system, which is 0 considered by IUPAC convention. So from these two value, now we can calculate the standard reduction potential of zinc. So E0 cell, that is 0.76, which is clear from this voltmeter, that will appear on the screen. Now this is equal to E0 of cathode minus E0 of anode. Now remember, by convention both are actually reduction potential. So first, for reduction potential, we will mention the E0 for H plus half hydrogen system, which is 0, and for E0 Zn2 plus Zn system, this is actually unknown. We are measuring this. This is unknown, but overall E0 is known, 0.6, and E0 for one of the half reaction, that is also known. So from this equation, we can find out that E0 of Zn2 plus Zn will be minus 0.76. Just you have to write this negative sign this side. So now it will be having this value. So applying this process, that is by taking She as the reference electrode, you can measure the reduction potential of any system by applying the same method. First you have to check what is the value that is appearing here. We have to put it in the E0 cell, that is the overall electrode potential that we are getting, and here reduction potential of one of the system is known, and other system you can easily know. And whether She will be acting as anode or cathode, that depends on whether electron is flowing from hydrogen system or it is flowing towards hydrogen system. depending on that it will be cathode or anode. So this is one of the example by which we can measure the standard electrode potential. We will also see that it is acting as anode. Another example also we will see. So here the cell representation will be Zn Zn2 plus. So this is the electrode, this is present in solution, this is aqueous, and this is anode. Normally this in cell representation this is not written, but for better understanding it is written here. 2H plus, which is in solution state, and here we have taken HNO3 for the source of H plus, and hydrogen will be produced, and this is the cathode side. So this is the oxidation half reaction, this is the reduction half reaction. Okay. Now as we have said that she can be cathode or anode, both are possible. So here what system we have taken? Now we have taken copper 2 plus and copper system. In the previous case we have taken Zn Zn2 plus, now we have taken copper 2 plus. So here the value that we are getting is 0.34 volt, and now the electron is moving from She towards the other half cell, which is copper 2 plus copper system. So now the electron movement is from She. In the previous case it is reaching towards She, but now it is from She. That means She is supplying electron. The deflection of voltmeter indicates that current is flowing from copper electrode towards hydrogen electrode, because the direction of electron is from She to copper electrode. So that is why the direction of current, as it is reverse compared to the electron flow, so obviously the current will be flowing from copper electrode towards hydrogen electrode, which is clear from the deflection of the voltmeter, because you can see this is the deflection of the voltmeter, and the electrons are moving from hydrogen to copper electrode. So this is opposite. So here this is anode, this is cathode. The hydrogen electrode acts as anode here and copper as cathode. So another example we have seen where She is behaving as anode. In the previous one it is behaving as cathode, but now it is behaving as anode. So now the two things we will compare simultaneously, that is hydrogen electrode that is present in the left hand side, that is anode. So electron flow will be from left to right, and the metal system, any general expression we have taken, suppose M is having oxidation state N plus, it is accepting N electron which is coming from She, and it is converted to the reduced metal form. So this is one possibility, and the electrode works as anode. So obviously half hydrogen will be written first, and then in the right hand side H plus plus electron. And here the another possibility, now in the anode we have Mn plus, and in the cathode we have She, and electron flow obviously it is always from anode to cathode. Now the reaction of She will be H plus is accepting electron, because now it is cathode, and we are getting hydrogen gas. Fine. Here we have a problem that a diagram is given, that is cell diagram. So we have to write from the cell diagram from this cell representation. Basically it is, you have to write the cell representation. It will be sorry, it is written wrong. It is already drawn. This is the cell diagram that is already drawn. We have to write the cell representation. It is written in a wrong way. Okay, I think it is clear that the cell diagram is given. So it should be written in this way, that write the cell representation from the cell diagram which is drawn. Okay. So what we have here, we have iron 2 plus system and iron 3 plus system. Okay, so this is a redox electrode type, that means same species into different oxidation state, and platinum, that is the inert electrode, and in the right hand side we have hydrogen. This is a standard condition, and here also platinum is the electrode. So how we will write it? Now you have to know what is the reduction potential value for this system, because we already know. So if you do not know, then it is not possible for us to write the cell representation, because here from this diagram it is not clear that which is anode or cathode, because we do not know what is the electron flow direction. So you have to know what is the reduction potential. Now as it is given that it is plus 0.77, which is more positive compared to She, that means it will be treated as cathode, because higher is the positive value, more will be the tendency to accept electron. So that is why it will be cathode. So first write She on the left hand side and Fe3 plus Fe2 plus system in the cathode side, that is right hand side. Now we will write the electrodes. In both sides it is platinum electrode. Then anode. So anode means increasing oxidation state. So here oxidation state is 0, here it is plus. And in cathode, Fe3 plus is the starting material, it is accepting electron and it will be converted to 2 plus. And finally we have to write this vertical sign. So this is solid, this is gas, this is H plus. So when there is a different physical state, solid, gas, aqueous, there is we use this single vertical, and this is a Sol bridge. And now Fe3 plus aqueous and Fe2 plus aqueous both are in aqueous condition, so that is why we have used comma here, not vertical sign, because they are in same phase. And then platinum. So in this way you can directly write it, but if you are thinking that first you have to select which one will be cathode or anode, after that you have to select what is the electrode, because in cell representation in the starting point and end point in both sides there is electrode, and then we have to choose what is the oxidation state in the species which is present in anode, that is initial oxidation state, final oxidation state, and also in cathode what is the initial oxidation state and final oxidation state. Here it will be decreasing because it is accepting electrons, so obviously 3 plus will be decreased to 2 plus. And finally if it is same phase there is a comma, in different phase there is a vertical sign. So in this way, if in the question some cell diagram is given, then also you can write the corresponding cell representation, provided these values should be given. Okay. Now this value you can get from electrochemical series. So in this process, just remember what we have discussed here. In this process we have find what we have find out finally, E naught of Zn2 plus Zn system. So in this way, if you find for different metal system or any other non-metal system what is the corresponding reduction potential value, by using She as reference electrode, then combining all these values we can make this series. Now look at this series carefully. This is the standard, that is reference electrode. So that is why it is highlighted and it is kept at 0. Now as we are moving upward, positive values you are getting. Gradually it is becoming more and more positive, and maximum positive it is for fluorine system, which is 2.87. And as you are moving down, basically you are moving from more and more negative. So maximum negative it is lithium system. So basically when you are moving down, you are reaching towards stronger reducing agent. That means this system which is at one extreme, it will have very high tendency to feed electron to other system, and as you are here in the other extreme, fluorine will have high tendency to accept electron from other system. So this is stronger oxidizing agent. Okay. Now in some books it may be the opposite, that is the positive values are written below hydrogen and negative values are written above hydrogen, but that will not be very problem, because you just have to be sure that whether it is becoming more positive compared to hydrogen, whether it is becoming more negative compared to hydrogen, whether it is present above hydrogen system or below, that is not important. The value is important. Okay. But in different places different types of that it can be mentioned in a different way. So sometimes it may be mentioned, suppose if you consider this table for electrochemical series, if I say that copper is present above hydrogen. Okay, now in some other book or in some other space you are finding another electrochemical series where the positive values are written below hydrogen. So in that case someone will say that copper is present below hydrogen. So be very careful this below and above, because it depends whether it is written above hydrogen system or below. But you have to be just sure that whether these values are negative or not. So if it is more negative, suppose two systems are given. One is this 0.77, which is for iron, 3 plus 2, 2 plus. It is not 2 plus 2, 0. It is 3 plus 2, 2 plus. And another is given this cadmium. So if this two system is given and if it is asked that which one will be behaving as anode, which one will be cathode, it is very easy to say, because here this will act as anode. It will always, it has a tendency to feed electron. That means it will lose electron, and electron will be gained by iron because it is more positive. Now higher you are, suppose you are choosing something from here and something from here, so it is the gap between these two systems is very high. That means higher will be the gap, higher will be the value. These values are negative, these values are positive. So when we will do the calculation E naught cathode minus E naught anode, this will be very high value. Okay, so remember, if the two systems are given, that is the corresponding reduction potential value. Just by looking at the value you can understand which one will be cathode, which one will be anode. The more positive it is, it has a tendency to gain electron, so it will be in the cathode side. That is reduction will take place. Okay, so this is the electrochemical series. There is different applications of electrochemical series. That is, if this series is given, we can get different types of information from this series, and it is better if you can remember some of these values, though in numerical you will find that mostly these values will be provided, but some systems which are very common and they are used very frequently, it will be better if you can remember these values. Okay, so there is so much importance for electrochemical series because it has so many applications. Fine.